Okay, so today we are going to continue with our examples of redox reaction. Okay, we are going to talk about rusting of metals, okay, rusting of iron in particular, okay. But before we can explain a little bit about rusting, we have to talk a little bit about corrosion. So when I talk corrosion of metals, okay, I must always remind myself the 4 definition of oxidation and reduction in terms of loss and gain of oxygen, loss and gain of hydrogen, transfer of electrons, and change in oxidation number. I am interested in number 3 here, transfer of electron. When I say transfer of electron, okay, oil rig should come to your mind. Oil is oxidation, okay, rig is reduction. Oil is loss of electron, reduction is gain of electron, okay. Once it's clear, you can start, okay. So corrosion is an example of a redox reaction, okay. What is the first step in corrosion of a metal? So the metal donates 2 electrons. If I'm using zinc, it donates 2 electrons to form Zn2+. The moment you donate electron, it's the oil, okay. So oil, so it must be oxidation. So what is the first step in corrosion of metal? The metal undergoes oxidation by donating electron to form a positive ion, okay. So you want corrosion to take place, there must be certain factors that you must think about, okay. So the rate at which a metal corrodes depends on 2 factors. One is the electropositivity of the metal. Second is the nature of the product of corrosion. Okay, when I say electropositivity of the metal, okay, you look at the ECS, electrochemical series, okay. You notice that these metals on top here, they are very electropositive. The moment I say they're electropositive, they have a tendency to donate electron and form positive ions. So these metals are easily corrodes, okay. This metal can easily corrode, okay. But if you go down, you look at silver, copper and all that, these metals are less electropositive, so they do not corrode easily, okay. So when you talk about rate of corrosion of metal, you remember the electropositivity, okay. The one higher above corrodes faster compared to the one below, okay. When then you talk about the nature of the product of corrosion, okay. So when you talk about nature of the product of corrosion, okay, so when a metal corrodes, it forms a metal oxide coating, okay. Example, zinc. Zinc will change to Zn2+, okay. Zn2+ combines with the oxygen in the air to give you zinc oxide. So this zinc oxide can be protective or non-protective oxide layer. It depends on the metal, okay. So let's take an example here, aluminium, okay. You look at aluminium. Aluminium combines with the oxygen from the air, okay, to form aluminium oxide. This aluminium oxide is very protective, okay, because it's tightly packed, non-porous, and firmly attached to the metal. So if you give it a knot, it doesn't break easily. So water and air, okay, water cannot seep through, air cannot enter. So the corrosion of the aluminium does not continue to the inside part, underneath, okay. So that means only the oxide layer is formed on top, and it protects the aluminium from further corrosion of the metal, okay. Other metals that have the same properties like nickel, chromium, tin, lead and zinc, all these they react with the oxygen in the air to form protective oxide layer, okay. You look at non-protective oxide layer. Non-protective oxide layer, there's one I think that you're very familiar, that is magnesium. I think you have done quite a number of experiments with magnesium in the lab. Okay, magnesium, okay, reacts with the oxygen in the air to give you magnesium oxide. But this is not a protective oxide layer because you can remove it easily with sandpaper. Do you realize that? Okay, another example is iron. So iron reacts with the oxygen in the air to form iron oxide, which is also a non-protective oxide layer. So why is it non-protective? It's not tightly packed, it's porous and weak and peels off easily. So the moment it peels off, the water seeps through, oxygen enters, and the corrosion continue to the inside part of the metal, okay, until the whole thing is gone, okay. So those are the 2 factors that affect the rate of corrosion, okay. Finally, we reach to what we want to learn, okay. We want to learn about rusting as a redox reaction, okay. When I say rusting as a redox reaction, okay, you remember, okay, the word rusting can only be used, okay, for iron. So when iron corrodes, we say iron rust, Okay, so what are the two conditions that I need for rusting to take place? I need oxygen and water, then rusting will occur. Okay, and then of course for rusting to take place, oxygen must be the oxidizing agent. What about iron? Iron must be the reducing agent. So you look at the diagram given down here to explain the mechanism of rusting. Okay, you have a water droplet and you have a piece of iron down here. So you notice the water droplet on the iron. Okay, you see the middle part here. The middle part here, the concentration of oxygen is not high. So at this part, what will happen is the iron first step in rusting donates 2 electrons to form iron 2+. The presence of the electron here make it a negative terminal, and since it's a simple cell, it is known as an anode. Okay, don't forget, negative terminal is known as anode. There is loss of electron. Okay, these electrons will flow through the metal to the edges of the water droplet. Can you see the edges of the water droplet? Okay, here you have a lot of oxygen dissolved in the water. So the oxygen that has dissolved in the water gain the electron to form hydroxide. Okay, so this happens at the edges of the water droplet. Okay, since you use your electron, this will be a positive terminal. It's known as a cathode. Okay, is that okay until that part? Okay, what happens after this? Okay, so you have a positive ion Fe2+, and you have negative ion, okay, hydroxide. So the positive and the negative ion, they will combine with each other to give you okay, what do they give? Okay, I'll show you the next page first. Okay, yeah. So the positive and the negative ions, they will combine with each other to give you iron 2 hydroxide. But iron 2 hydroxide is green in color. Since it's green in color, okay, further oxidation by oxygen in the air changes it to rust. Okay, rust is hydrated iron 3 oxide, Fe2O3.X H2O. Okay, the X here is an integer and the value of the X varies according to where the rusting is taking place. This hydrated iron 3 oxide is brown in color and it is known as rust. Okay, it's known as rust. Okay, let's do the first step. The first step is the middle of the water droplet. Okay, so the electrons flow to the ends of the water droplets. Okay, hydroxide is formed. So the iron 2 combines with the hydroxide to give you iron 2 hydroxide, which is green in color. Further oxidation changes it to iron 3 oxide hydrated, okay, which is rust, which is brown in color. Okay, next. Okay, so the rust that is formed on the metals, let's say you have some metals, some iron at home, the rust that is formed, you notice the rust is very brittle, it's porous, got a lot of holes and not tightly packed. Therefore, the water can seep through the metal underneath and rusting continue to occur. Okay, so it has a non-porous protective layer. Okay, it has a porous non-protective layer. Okay, so the water can seep through inside. Okay, but you notice also that if you want your iron structure to rust, okay, to rust at a higher rate, okay, this will happen in the industrial area. Because industrial area, you have chlorine, sulfur dioxide, nitrogen dioxide in the air, okay? These gases, when they dissolve in the water, they make the water a better electrolyte. There is the presence of free moving ion, okay? And hence, they increase the electrical conductivity of the water. Since they increase the electrical conductivity, we notice that rusting occurs at a higher rate. The same is true for coastal area. So if you talk about coastal area, you notice coastal area also rusting occurs at a higher rate. Okay, the reason it occurs in a higher rate because in the water you have salt. Okay, what salt do we have? We have sodium chloride. You notice the sodium chloride here, and then this is the hydrogen bond with the water. So the formation of these ions, okay, make it a better